The next paper will be advantages and disadvantages by biarticular actuators in bipedal robots. And the authors of this paper are Atabak, Nezhadfard, Karsten, Berns, and Patrick Vonwirth. Who is going to be the presenter here? Can I invite you to present the paper? Which is it, Professor Nezhadfard, who is presenting? Ah, I see the paper. Yes. Okay, author.
Hi everyone, I hope you can hear me.
Yes.
Perfect. I just try to...
Your name, please. Yeah.
I'm Nezhadfard. I don't know if... okay. So, I hope everyone can see. Okay. So, I start. I'm Nezhadfard. I am from TU Kaiserslautern. Today I will present the advantage and disadvantage of the biarticular actuators in the bipedal robots.
Yes.
So, in our robotics lab, we have designed this planar robot called Carl. The planar robot has 3 actuators, 3 mono-articular actuators. You can see it in the back side of the leg. They are classic actuators that are connected to each joint. In extra, we have 2 additional actuators that are called the biarticular actuators. These biarticular actuators, like now you can see the laser pointer, will be easy to show. So these are the biarticular actuators in front, and these biarticular actuators are connected to 2 joints. For example, this one is connected to the hip and knee, and this one connected to knee and ankle. So when they are activated, generate torque in 2 joints simultaneously. This is the way that the redundancy of the actuation system exists in our human body, and we want to bring this into the robotic bipedal leg. So we also designed the actuators, series elastic actuators in our lab. I will describe them in the next slide. So in this video, you can see that we have series elastic actuators that have a ball screw transmission. This ball screw transmission gives us 95% of the efficiency. It's very small friction, and it helps for back drivability of the actuator. We also have a very small reflected inertia. You can see that compared to the other actuators, state-of-the-art actuators, we have very small reflected inertia, and therefore the system is very good, very back drivable, and a very high efficiency of a good performance of the force control. So why we have a biarticulars in our body, and why we want to bring it into the robotic leg? And the main advantage of the biarticular muscles is the transfer of power. As you can see here in a paper from Jacob, it shows that during the jump motion, 21% of the power needed in the knee is transferred by the biarticular from the hip. The similar power transfer happens from the knee to ankle via this muscle here, which is 25% of the amount of power needed in the ankle. It's quite important, this power transfer, because if we want to consider the jumping in human, only 50% of the power needed in the ankle joint can be generated by our muscle, shank muscle. The other 25% has to be delivered from the knee, and the other 25% has to be generated by the Achilles tendon. So if you assume that the 25% of energy is transferred by the biarticular, by a rough estimation, we can say that the mass of the muscle connected to our shank can also reduce by 25%, like something like this. So indeed, having biarticulars helps to have a better mass distribution in our leg. You can see that bigger muscles always attached to the trunk and the thigh, and the smaller muscles are placed on the shank and the distal side. This is the way that human leg can have a better agility and efficiency of the movement. And the last important feature of the biarticulars is that they are designed in a way that they generate very low velocity. They experience low velocity during the movement. For example, during the explosive jump movement, biarticulars experience 30% of the velocity of the mono-articulars. This is quite influential for designing a biarticular actuator. The decision on the gear ratio and the moment arm of the biarticular actuators. So as an overview, I will show how a robotic leg during the jump experiment can transfer the power. So this helps us to understand the advantage of the biarticulars. I also discussed the moment arm profile of each actuator and what is its significance when we are designing the actuators. And these are the important effects for understanding the advantage and disadvantage of the biarticulars. In the end, I will show the maximum ground reaction force due to having a biarticulars in our body, and what happens if we don't have it, and so on. So what is the moment arm profile? As you can see here, if we have a linear actuator, the moment arm of a linear actuator around the joint is always a nonlinear value. And you can see that in some postures, our actuator is able to generate high amount of torque. This has a high moment arm. And in some postures, it loses its mechanical performance. The moment arm matrix defines the interaction between actuators. So for example, and here you can see the formula that the moment arm matrix is just a mapping from the force domain or from the actuator domain to the joint domain, the torque of the joint. Similar mapping is between the velocity domains using the moment arm matrix. This moment arm matrix is each component is one of these nonlinear profiles. So, for example, assume that we want to generate the torque in the knee here, and if we generate the torque in the knee, the actuator, mono-articular actuator that's connected to knee will be activated. However, there will be a biarticular also connected to knee that activates and generates a side effect torque in the hip. This side effect torque has to be compensated by the mono-articular in the hip. Similarly, this same torque can be generated in the ankle via the biarticular in the ankle, and the mono-articular in the ankle has to be activated to compensate this. As you can see, all the actuators has to be activated to only generate torque in the knee. This network of the actuation system is very important for the design. It has to be considered, and it is described by this moment arm matrix that I show here, AM. So we designed the actuators, moment arms of the actuators, trying to replicate human. You can see here that they are they are more or less have the same profile. The size of the these magnitudes are different because the human muscles generate higher forces, so they have a smaller gear, smaller moment arms. As you can see here, the moment arm in the hip follows gluteus maximus muscle. The moment arm of the knee follows vasti muscle group, and the moment arm in the ankle follows soleus. We have a 30-degree differences between the soleus and ankle is because of the missing degree of freedom in our toes. So since the robot does not have this toe joints, which is called MTP joint, therefore we have to make 30-degree differences to be able to perform the motion task that is needed for walking and running and locomotion. So one of the side effects of the biarticulars is to have a small moment arm compared to the human muscle. So here is the human muscle moment arms, and you can see that we achieve much smaller moment arm with the biarticulars. This reduces the capability of the actuator to generate torque in the joints. The reason to do for this is that the actuators are spanning two joints. So, and each joint has a 100-degree, 150-degree of range. So these actuators, for example, the actuator that is connected to hip and knee has to have a range of 100-degree for the hip and the 100-degree for the knee. And this reduces its moment arm. Similar for the ankle and knee biarticular in the lower part of the stage. So if we compare the energetics of the jumping movement of the robot with the human, you can see that we can achieve similar behavior from the biarticulars if they designed correctly, of course, in a way that the power transfer happens from the hip to the knee, and also power transfer happens from the knee to the ankle. It is similarly reported in human, but in human these power ratios are different. One of the major reasons is that the dynamics of the robot and the human is different. We do not have a trunk in the experiment that we show, so the power distribution between joints would be different. But as I can show here is that biarticulars are advantageous because they can transfer the power both in human and both in robot. So here I put the values of these power transfer. For example, the biarticular between hip and the knee takes 24 joules energy from the hip, transfers to the knee, and meanwhile generating an extra positive 24 joule of energy. Similarly, there will be 10 joule transfer from the knee to ankle, and also generating positive extra 7.8 joule of energy. This transfer of energy, again, is reported similarly in humans. There is another advantage of the biarticulars, which is about the maximum force, ground reaction force that the leg can generate. These biarticulars can increase the maximum ground reaction force and therefore can improve the performance of the leg to compensate its weight, the body weight. So, for example, here the red polygon are a Carl is a virtual Carl leg that has a 50% stronger mono-articular actuators. Does not have a biarticular, it's mono only, but has a 50% stronger actuator. If we have, you can see that this acts similarly to Carl, which is the black polygon, that has two biarticulars and the mono-articular is 50% reduced. The this also means that we can, by distributing properly the mass over the body, we can achieve similar ground reaction behavior as by just increasing the 50% only the mono-articular actually. One of the benefits of the biarticulars is that it can act as an alternative for the dual actuation, dual motor systems. In this, here I show a paper recently published about a dual motor systems in which one actuator consists of two motors. One motor is for the fast movement, which requires low gear ratio. The other motor is for slow movement and high torques. So they have two motors to perform in a different operating points, operating conditions. If we have a biarticulars, we can alternatively have a redundancy. Instead of having two motors in one actuator, we can have two different actuators. Mono-articular actuators can act for fast movement and the low gear ratios. And on the other hand, biarticulars can act as a slow actuation system with a high gear ratio. This, as I showed in human, also the biarticulars act slowly. So this way also we can improve the mass distribution in the leg. Rather than putting all two actuators in one point, we can distribute the mass also throughout the body and also reach a better bio-inspired leg. So in conclusion, I want to say that at the end, we end up with a trade-off between the high mass and efficiency. If we increase the actuator redundancy, means that we are increasing the mass of the leg by adding the redundant actuators. However, by adding the redundant actuators, we can also improve the efficiency. So the whole thing comes to a trade-off between these two, and also depends on the type of the actuators that we are selecting and locomotion type that we choose. As I showed that as an advantage, the power transfer happens in leg. We can achieve similar in the robotic leg. We will have a better mass distribution, especially for the shank actuators and shank muscles. We can achieve a better bouncing movements like running and jumping with the leg. The articulars can be deployed as a high gear ratio slow actuators, and it could be an alternative for a dual motor system. The disadvantage is that the articulars will have a smaller moment arms compared to mono-articulars, and therefore their torque possibilities, their efficiency will be also decreased. On the other hand, it is not shown any power advantage of the biarticulars for walking locomotion. Unfortunately, it is shown that there is no clear evidence that the biarticulars can help for walking. This is from the power transfer, but I do not know about the technical benefits of a biarticular actuator. So this is something that has to be considered when we are designing a robotic leg. When we are trying to copy human, some stuff we may miss. And this is one part that we have to identify if there is a technical advantage for the biarticulars in a robotic leg or not, considering walking locomotion. So at the end, I'm finished with the presentation. I thank everyone to listening to me and joining this presentation. And of course, I'm ready to answer all the questions.
Okay, thank you, Atabak Nezhadfard, for a very interesting and comprehensive presentation. And I'll invite questions quite quick because we're falling a little bit behind time. So questions, please. Hello, any questions?